Hi, for my reproducibility challenge, I've chosen to reproduce learning latent dynamics for planning from pixels. This is a reinforcement learning paper published in ICML in 2019. So first, I'm going to summarize the paper by going over some of the main contributions of the paper, like the recurrent state space model and latent space planning. I'll then go into the experiments I performed and discuss what did and didn't work. So this paper introduced PlaNet, a model-based reinforcement learning agent. It achieves comparable performance to model-free agents with 200 times less environment interactions. The main contributions of this paper include the recurrent state space model, which represents the latent dynamics or model of the environment and contains both deterministic and stochastic components, a planning algorithm that uses the model to decide on behavior, and latent overshooting, which is a technique to modify the objective function so that the gradient of a state transition is backpropagated into multiple paths to better enable multi-step prediction. However, the authors found that PlaNet does not benefit from latent overshooting, and they did not include it in the final version of their agent. Thus, I will not attempt to reproduce this contribution. So this is an overview of the recurrent state space model, or RSSM. The gray circles are given to us as inputs, the squares represent deterministic nodes, and the circles are stochastic nodes. Solid lines denote the generative process, and dashed lines denote using the RSSM model to do inference. So how do we compute these nodes? The states are computed by the following models. The deterministic state model produces the deterministic state. The encoder, which extracts a 1024-dimensional feature vector from the images. The stochastic state model takes the 1024-dimensional feature vector and produces a low-dimensional 30-unit stochastic state. The observation model, or decoder, reconstructs the image observation from the latent state. Finally, you have the reward model, which predicts the reward from the latent states. So how do we represent all of these models? They are all represented as Gaussian distributions parameterized by fully connected neural networks with ReLU activation functions. The deterministic path has 200 units, whereas the stochastic path has 30 units. Moreover, the encoder uses convolutional layers to extract features from image inputs, and the observation model or decoder uses transposed convolutional layers to reconstruct images from the extracted features. To learn the models, we define the loss as the sum of the variational lower bound on the data log likelihood, which includes the KL regularizer. We also add the loss of the reward model. And because we are sampling from a probability distribution, we also need to employ the reparameterization trick in order to backpropagate through the random variables. Also, by letting our models be Gaussians, we can represent the loss as the mean squared error between our model outputs and the actual image observations or reward. The next main contribution of the paper is the planning algorithm. The sole responsibility of the planner is to come up with the best action that maximizes the agent's reward. The planner uses the RSSM to predict many different features in latent space. Since the latent states are low-dimensional, the planner can efficiently predict thousands of different feature state action trajectories. The planner is based on the cross-entropy method, or CEM, which I'll get into on the next slide. The planner also uses model predictive control, or MPC, which just means that the planner optimizes for a single time step at a time. So for each time step, the planner will have to call the planner each time to come up with an optimal action. In the next time step, everything resets, and we will have to call the planner again for the next action to take. Okay, so what is the cross-entropy method? The cross-entropy method is a population-based optimization algorithm. For PlaNet, we initialize a distribution over action sequences. We then sample thousands of different action sequences from an action distribution. Next, we minimize the cross-entropy between the current distribution and an optimal action distribution that gives us actions that produce the most reward. By doing this, we are hopefully able to sample better action sequences in the next iteration. If things are still unclear, hopefully the next slide will clear some things up. So this is an overview of the planning algorithm using CEM. With the RSSM as input, we first initialize the action distribution to be a standard Gaussian. Then we sample j equals 1,000 different action sequences from this distribution, and for each sequence, predict 4 of the future states and rewards in latent space using the RSSM. Then we set the parameters of the action distribution to be the average of the k equals 100 best action sequences that have the best reward. We repeat this process for 10 iterations, and then return the mean of the first action. This algorithm gives us an action to take at a single time step. For the next time step, we repeat this process again since we're using model predictive control. So I've covered the main contributions of the paper, and this is a high-level overview of the PlaNet algorithm. We first gather random seed data by letting the agent perform random actions. We then define and initialize all of the models as Gaussians parameterized by neural networks. We then alternate between model fitting, which learns the RSSM, and data collection, which uses the planner to collect new data. So my goal was to reproduce the results on the cheetah run task in the DeepMind control suite. I chose to do this task because compared to the other tasks, this one has a relatively low variance in results and converges pretty quickly, as depicted in the graph on the right, which is taken from the paper. So this is what the task looks like when the agent is performing random actions. In this task, the actions are 6-dimensional vectors that control the joints of the cheetah, and the agent gets rewards by moving forward. This is what the task looks like when the agent is performing optimally. And this is what my agent looks like. At times you can see that it takes a small leap, but clearly my agent is far from optimal. This is a summary of the results. I trained the agent for 150 episodes and compared this to PlaNet's performance after 150 episodes. So my agent is approximately 10 times better than doing random actions and about 20 times worse than PlaNet's performance. So what went wrong? One of the biggest discrepancies was the training time of my agent versus the author's agent. And the big time cost has to deal with the runtime of the planning algorithm, which is used in the data collection process. So in the data collection process, we need to collect one episode of data. And each episode is 1,000 time steps, which means 1,000 divided by the action repeat number of calls to the planner. Each call to the planner takes approximately 1 second. And so the time to collect one episode of data, taking into account the action repeat, is about 250 seconds or 4 minutes per episode. Now we have to collect 150 episodes, so the runtime of the entire algorithm has a lower bound of 10 hours. This is a huge discrepancy when the authors state that training an agent on a task for 1,000 episodes should take on average 15 hours. I do believe that I followed the algorithm in the paper very closely, but yet my implementation is still very slow. This leads me to believe that either the author's implementation doesn't exactly match with the paper, or the more likely case is that they're using optimization techniques that I'm just not aware of. Here we have the loss curves of my agent. In the top graph, you have the loss curve, which has this really large spike in loss at episode 49. The bottom graph is the loss curve after removing episode 49. I'm not really sure on what the cause is for the spike, but the bottom graph does signal that the agent should be learning. But despite the loss decreasing, it did not result in an increase in performance, as this is my reward graph, and clearly it is not increasing over time. To try to gain insight as to why my agent's performance wasn't increasing, I decided to test the RSSM on its ability to reconstruct images. So as input, I gave the image frame on the top, a random action, and tensors of zeros for the initial deterministic and stochastic states. And the output was the reconstructed image on the bottom. Considering the fact that the model received zeros for the initial states, I think that the model did a decent job of reconstructing the image, and this implies that the RSSM is learning and working as intended. Ultimately, I'm still not sure why my agent's performance isn't increasing. Thanks for watching.